Hi everyone. In this video I'm going to demonstrate principal axis factor analysis using SPSS. Before we get started with our example, I want you to note that underneath the video description will be a link to the data that's being used in this presentation, as well as a copy of the PowerPoint presentation that I will be referencing throughout the video. So be sure to download both and follow along. So for our example, we're going to be factor analyzing 24 survey items where participants rated their level of agreement using a scale ranging from 1 being strongly disagree to 7 being strongly agree. You'll notice in this slide that I basically have the data view up here. This is in SPSS. These are the variables that are listed. This is just a subset of the variables, and then each row represents a given case. Then under variable view, you can see down here where we have, I actually have included the actual items in the SPSS data file so that you can interpret those a little bit quicker when you are interpreting the factor loadings. But to give you a little bit better idea, let's just kind of look at some of the items. The first one, in general, I am uninterested in politics. The second, I would rather turn off the television or radio than be exposed to people debating about political issues. So a number of these items are really representing sort of an engagement or an involvement and interest in politics. And then some of the items are actually derived from Bob Altemeyer's dogmatism scale. So some of those items would include, I may be wrong about some of the little things in life, but I am quite certain I'm right about all of the big issues. Someday I will probably think that many of my present ideas were wrong, that second one being a reverse-coded item. Now before we get on with actually analyzing the data using SPSS, let's consider some steps when carrying out exploratory factor analysis. So step one, you need to consider the question of whether or not it makes sense to carry out factor analysis on the correlation matrix. There are various ways of assessing this. Tabachnik and Fidel suggest examining the correlation matrix for the measured variables itself, and then if you have no correlations that are found in excess of 0.30, then there's not much point in carrying out the analysis. Additionally, through SPSS, we can ask for the Kaiser-Meyer-Olkin measure of sampling adequacy, and also Bartlett's test. And so basically if Bartlett's test is significant, this would be an indication of the factorability of the matrix. And then with the Kaiser-Meyer-Olkin measure, there are various thresholds basically stemming from Kaiser and Rice's review or suggestions. Basically KMO values that are in the 0.5s would be considered miserable, 0.6s would be considered mediocre, 0.7s are middling, 0.8s meritorious, and 0.9s marvelous. So basically anything less than 0.5 would be taken as unacceptable for carrying out factor analysis. And then obviously the closer you are getting to 1 indicates greater factorability of the matrix. Second, we want to consider the individual items and their contributions to the relationship in the matrix and the potential factor solution. So Andy Fields suggests that if a variable exhibits no correlations greater than 0.30 with the other variables in a matrix, then we should consider deleting those variables. Additionally, we can consider the measures of sampling adequacy for the individual items, which can be done by examining the principal diagonal of the anti-image correlation matrix and then relying on Kaiser and Rice's system for judging those measures of sampling adequacy. Next, we also want to address the question of whether multicollinearity may be a problem. So one way of doing this is to examine the determinant of the correlation matrix, and values that are found close to 0 may signal a problem. Andy Fields suggests a threshold of 0.00001 as a means of identifying potential problems with multicollinearity. There are some additional approaches that you could consider, which would include examining the bivariate correlations among your variables and seeing if there are any correlations that are falling in the 0.8s or 0.9s, which may signal a problem. And/or we could examine the R-squares after we regress each variable onto the remaining variables in your analysis. And this is an approach that's actually suggested by Tabachnik and Fidel. So once you've identified or determined that it is appropriate to carry out the factor analysis, then the next question that you want to address is how many factors account for the correlations among the variables. So potential considerations or strategies might include using the eigenvalue cutoff rule, and this is actually not generally recommended with exploratory factor analysis. It tends to be utilized more often in the context of principal components analysis. We also have the scree test, parallel analysis. Another option is to retain as many factors as a certain percentage of the variation. And then there's also factor meaningfulness. And some of these approaches are reviewed in Pidcock and Stevens' multivariate text. Finally, you want to name and describe those factors that you retain. And so this typically involves performing some type of rotation and then interpreting the factor loadings. So factors are named by considering those measured variables that load at some minimum threshold, whether it be 0.3, 0.32, or 0.40. And actually, Pidcock and Stevens suggest a threshold of 0.40. Okay, so here's our data opened up in SPSS, and let's go ahead and begin running our analysis. So what I'm going to do is go up to the Analyze button right here, go down to Dimension Reduction, and then Factor. Next, I'm going to move all of my variables over from the box on the left to the box on the right. And under Descriptives, I'm going to ask for univariate descriptives. I can ask for the correlation matrix to examine the relationships between the measured variables themselves. I can also request a determinant. I can request on KMO and Bartlett's test of sphericity, and also the anti-image correlation matrix that I was mentioning a couple of minutes ago. So next we'll click on Continue. Under Extraction, I will click on Method, Principal Axis Factoring right here, and I will click on Scree Plot. Now you'll notice that by default the extraction is based on the eigenvalue cutoff rule, and we're just going to leave that alone for right now and go ahead and proceed. Now it's oftentimes the case that when people are kind of clicking through, it's very easy just to go ahead and click on rotation and select a rotation strategy, but I kind of prefer to wait until I have sort of explored that issue of how many factors to retain before I go into this area. So I'm going to just click off of that, and then the next thing I'll do is I'm going to click on the OK button right here. So you'll see in our output with descriptive statistics, you can see that we have the means and standard deviations, and then the total effective sample size in this case is 253. So just kind of keep in mind that in this case listwise deletion was used, and so that's our total sample size. So now as I kind of scroll down, you'll also see right here that we have our correlation matrix, and there's a lot of variables, and because of that there are a lot of correlations among our measured variables. So I will say that in general you can see that we have a number, really a pretty large number of correlations in this matrix with values above 0.30, which would signal that yes, it's probably going to be appropriate to carry out the factor analysis on this correlation matrix. Also, as you kind of go through it, which again I'm not going to go through every one of these, but just to say that the correlations, none of them actually fell into the 0.8s or 0.9. So it's kind of unlikely that we have a problem of multicollinearity as well. So next we'll scroll down to this box right here. Oh, actually, let me just kind of note, underneath the correlation matrix you can see the determinant. It says 1.274. The E-5, that's scientific notation, but basically this value right here for the determinant of the matrix is greater than Field's threshold. So again, that would be some indication that multicollinearity is not going to be that much of a problem. Next we have KMO and Bartlett's test. You can see Bartlett's test of sphericity. You can see that it is statistically significant, and we would infer then that our correlation matrix is significantly different from an identity matrix. And basically an identity matrix just has the ones along the principal diagonal and zeros on the off diagonal, which in that case would signal no relationships among the variables. So the fact that our sample correlation matrix is significantly different from the identity matrix is taken as an indication that the matrix is factorable. And then we also have the KMO measure of sampling adequacy. The value is 0.87. So using Kaiser and Rice's language, we would say that this the correlation matrix is quote-unquote meritorious. So in short, we have evidence again supporting the factorability of the matrix. Next, where we have anti-image matrices, I'm going to scroll down here, go to the anti-image correlations. In the principal diagonal of this matrix right here, you can see we have the superscripts with A's right there. These are the measures of sampling adequacy for each of the individual items. Basically, using Kaiser and Rice's criteria, effectively, the items really seem to be appropriate for inclusion in the factor analysis. I think the lowest measure of sampling adequacy that we have is this 0.729 right here, but most of these values are all in the 0.8s and 0.9, so we're in pretty good shape with respect to the items that are included in the factor analysis. So scrolling on down, you can see that we have our table right here. And basically the results that are given in this portion of the table, this is actually based on an initial principal components analysis. And so you can see the eigenvalues that are associated with each of the components, but in this case, they're labeling them as factors. And the scree plot that you see below is actually a plot of those quote-unquote factors plotted against the factor numbers. So looking at our scree plot, you can see that clearly there's one dominant factor here, another dominant factor, and then you can see that a possible third factor, and then maybe even a fourth factor right here before things sort of level off in terms of the remaining eigenvalues. So probably somewhere in the neighborhood of a 3 or 4 factor solution may be appropriate for summarizing the data. Now, if we want a little bit more rigorous approach to identifying the number of factors, we can also use parallel analysis. And there's a nice little engine at this link right here, which I will include underneath the video description as well. And so basically what we're going to do is generate random eigenvalues and then essentially compare those random eigenvalues against the eigenvalues generated from our data. So up here where it says number of variables in your data set to be factor analyzed, I'm going to change this to 24 because we have 24 variables that are being analyzed. The sample size, I'm going to change this to 253. That's our, in this case, that's our listwise sample size. Type of analysis. Now you'll see by default it says principal components. And there's actually another option in here which is factors right here, but what we're going to be doing is comparing the eigenvalues from the initial principal component solution against random eigenvalues that are generated here. So this is a common approach is essential to identifying factors is to essentially use sort of a principal component solution first in order to sort of come up with an idea and then force that solution later on. Although it is also possible to perform the parallel analysis using the principal factors approach. Number of random correlation matrices to generate, I'm going to set this at 500. And you can see right here we've got percentile of eigenvalues. There's really two approaches that we could take when it comes to comparing the random eigenvalues against the eigenvalues from our data. One is to take the mean of the randomly generated eigenvalues across those 500 samples, and that's reflected in this column right here. The other approach is essentially using a percentile, in this case using the default 95% percentile. So you can see right here that once I've made all these specifications, the values in this table all change accordingly, and so now I can compare these randomly generated eigenvalues against the eigenvalues from our data. So going back to our data, and I've actually just kind of shrunk this window right here, but you can see the percentile eigenvalues basically for that first component right here, the eigenvalue from our data is 6.164. It is greater than a randomly generated eigenvalue at the 95th percentile of the randomly generated eigenvalues for the first component. Then you've got the second eigenvalue from our data is 4.567. You can see that it exceeds our the 95th percentile of the randomly generated eigenvalues for the second component. Then we have the third one, 1.806. You can see that value exceeds this value right here. And then the fourth one, 1.375, you can see that now that actually falls below the randomly generated eigenvalues. So what that would tell me is that if I'm going to make a cut, it's going to be a cut after the third eigenvalue. So basically all of the remaining components in this particular case are going to be sort of thrown out. So we're going to basically treat this as an indication that we should adopt a three-factor solution. So with that in mind, what I'm going to do is I'm going to stick with force a three-factor solution. So I'm going to go back to analyze, dimension reduction factor. Just in the interest of getting a little bit less information in my output, I'm going to select off of these because we've already addressed these issues. All of those would be the same values if we reanalyze the data in the way that we're about to do it. We'll go back to extraction right here again, principal axis factoring, but in this case we're going to click on this button right here and I'm going to type in a 3 right here and then click on continue. Next, we are also going to want to rotate our factors. So I'm going to click on this button, and so there are two general classes of rotations. There's orthogonal rotation and oblique rotation. And orthogonal rotation essentially maintains the orthogonality of the factors following rotation. So once you've basically carried out the factor analysis prior to rotation, the factors are uncorrelated with each other. And then if I choose an orthogonal rotation, there will still remain no correlation. And so one common approach is Varimax right here. So I'm going to click on that, continue. Under options, this is kind of a handy thing to do. You can also click on suppress small coefficients, absolute value below, and you'll see that by default it's 0.10. But I'm going to be using a loading criteria of 0.40. That's actually kind of recommended by Piddock and Stevens in their book, and I think that's a good criteria to adopt. So I'm actually going to set this at 0.40. And so what's going to happen is that in my loading matrices, any values, any loadings that fall below that number, it's just not going to appear. And that can be really handy when it comes to trying to, find when it comes to naming the factors. It doesn't mean that there are no loadings. It just means that we're hiding things that are really fundamentally distracting. So what I'm going to do now is click on continue and then on OK. So scrolling down, you can see that now where it says total variance explained, extraction sum of squares, you can see that we have the eigenvalues using the principal axis factoring, and then we have percentage of variance accounted for by each factor. So you can see the first one accounts for 23.6%, the second one accounts for roughly 17%, the third one about roughly 5.3%. So the three factors account for roughly 45.6% of the variation. Then over here you've got the rotation sum of squares. So right here you've got essentially the eigenvalues following rotation, the percentage of variance accounted for by the factors following that rotation, and then you can see right here that the cumulative percentage should be the same both pre and post rotation. So scrolling down, you'll see that factor matrix, that is the unrotated loadings, and I'm going to actually scroll down and go to the rotated factor matrix, and you can see that the values, these blank boxes right here, it doesn't mean that there are no loadings. It just means that these loadings did not meet the loading criteria of 0.40, and we suppressed them to kind of clean things up and make it a little bit easier to interpret. So as you can see, the first question, in general, I'm uninterested in politics. You can see there's a negative loading. It's negative 0.694. The second one, I would rather turn off my television or radio than be exposed to people debating about political issues. The third one, I like to interact with people who enjoy discussing political issues. There's a positive loading there. The next one, I enjoy learning about world events and the role my country plays in them. There's a positive coefficient. I like watching television and radio concerning political issues. There's a positive coefficient. So you can see that basically all of these items right here in this area essentially reflect sort of an engagement or basically an interest and involvement in politics. And the positive coefficients are reflecting the sort of affirmative wording of that sentiment in terms of being interested and involved. And then the negative loadings that you see right here, and down here really reflects sort of the opposite sentiment, which is complete disinterest. So if you think about a single dimension reflecting level of interest and involvement, you would have, essentially low interest on the low end and then high interest on the high end. So at any rate, those items that are sort of reflecting the opposite of interest, that's why you have these negative loadings that are given right here. So scrolling down a little bit further, you can see that we have some items that are loading right here. Anyone who is honestly and truly seeking the truth will end up believing what I believe. Things I believe in are so true, completely true, I can never doubt them. My opinions are right, will stand the test of time. All of these are essentially positively worded items from Altemeyer's dogmatism scale. And then there's this one item that's sort of standing out by itself. I am a long way from reaching the final conclusions about central issues in life. That actually has the lowest loading on the factor. So in general, what it looks like is that these items largely reflect sort of a dogmatic certainty. When you look at the next factor right here, you've got the things, there are so many things we have not discovered yet. Nobody should be absolutely sure of his beliefs are right. I have never discovered a system of beliefs that explains everything to my satisfaction. You've got flexibility as a real virtue in thinking, since you may well be wrong. So this is kind of reflecting the idea of belief flexibility. So you can basically think about factor one, based on this review, as reflecting political interest and involvement, factor two reflecting sort of a dogmatic certainty, and then factor three reflecting more or less a belief flexibility. So now let's reanalyze our data, but instead of using Varimax rotation, we're going to use Promax rotation. So I'm going to go down to dimension reduction, factor again. We'll click on rotation, and we'll use Promax. And this is basically an oblique rotation, and it allows for our factors following rotation to be correlated. So I'm going to click on continue and then on OK. So we're going to leave everything else the way they were, and you'll notice that in our table right here, you've got rotation sum of squared loadings. This portion of our box right here is going to be the same as what we had before, but these eigenvalues right here are really not accounting for the fact that our factors are actually correlated with each other. And so that's why you don't see the percentages of variance that you saw before when we performed orthogonal rotation, basically using our Varimax rotation approach. So that's why that information is not given in this particular portion of the output. So as we scroll down, you'll see that we have a pattern matrix and a structure matrix. So the structure matrix just basically reflects the zero-order correlations between each of the measured variables and the retained factors. And unfortunately, though, it does not reflect the relationship between each variable and the factor controlling for the intercorrelations among the factors. So this is probably not the best matrix to focus your attention on when it comes to interpreting the factor or naming the factors. So really a better matrix to kind of pay most attention to is the pattern matrix. That's actually sort of that's more endorsed by a number of authors, including Piddock and Stevens in their book. And so you can see right here that with the pattern matrix, essentially the loadings are reflecting the relationship between a given measured variable and a factor, controlling for the fact that these factors are all allowed to correlate with each other. So it gives us, so that you can think about the loadings as pretty much analogous to standardized beta weights in the context of regression analysis. And you'll notice that basically in this particular instance, or this example, all of these loadings are on factor 1, and they basically reproduce what we found before, which is sort of that interest and involvement in politics factor. Factor 2, you can see essentially the loadings reflect the idea of dogmatic certainty with respect to one's beliefs. One notable difference right here is that item that was negatively loaded, you can see that it does not even appear in this particular output. And then for the third one, you can see that these loadings all reflect essentially that flexibility, our belief flexibility factor. As we scroll down a little bit further, you can see that we have a factor correlation matrix, and you can basically interpret the correlations as reflecting the correlations among those factors that we had before. So you can see that first factor was essentially the interest and involvement factor, and you can see it's correlating really low with the dogmatic certainty and flexibility factors, but you do see that there's a negative correlation. It's a negative 0.352 between the dogmatic certainty factor and our belief flexibility factor. So that pretty well concludes this demonstration. Again, be sure that you download the SPSS data file and the PowerPoint that I provided as links underneath the video description. And if you like this video and the supporting materials, please take time to basically click the little like thumb on the YouTube site and share the video with others. So I appreciate you watching.